Okay, hey folks, we're going to start getting into real gas behavior. And to first start that, I want to talk briefly on the compression factor and how we can use this as a metric for quantifying real gas behavior. So this will be pretty short, followed by some longer videos getting into more details. So the first thing that we can start to say about real gases is they interact, right? And that interaction is through their intermolecular forces, right? So through hydrogen bonding or London dispersion, etc. So we can view that interaction as a distance-based quantity, so how much distance there are between molecules. So for example, if we plot the potential energy between molecules on the y-axis and their separation on the x-axis, zero potential energy here, so let's highlight that line, that would correspond to two molecules or atoms, right, that are spaced far enough apart that they have no interaction with each other. So they truly are ideal. But as we force them to get closer together, right? So now they're getting closer and closer, right? And it's important to note that this is not showing bonding, right? This is intermolecular forces. There will be a certain critical separation that gives you a maximum attraction, okay? And if we try to squeeze them too close together, then the repulsions will begin to dominate. So, and what we would expect out of that is when we have put the molecules too close together, they're going to want to push each other apart. So that will owe to viewing expansion relative to what an ideal gas would show. And if we're in this attraction regime, the molecules want to get closer together. So that would be viewed as compression relative to the ideal gas regime. So we're going to use this thing called the compression factor to quantify that. And the compression factor goes as following. It's a capital Z, and that is equal to the quantity Vm divided by Vm naught. So we're going to start getting used to seeing this per m quantity. So when we see that in this class, we can always replace that with number of moles. So Vm equals V divided by n. And so this quantity on top would be our observed volume per number of moles. This quantity on the bottom here is our ideal value. And of course, at STP, hopefully you remember, or approximately remember, that this value is 22.42 liters per mole at STP. But if we're not at STP, we could also calculate it, right? So we know from the ideal gas law, PV equals nRT. Well, we've already got that N taken care of. So the ideal way of writing this would be Vm, let's see, equals RT over P. And thus, it doesn't necessarily have to be 22.42 liter per mole. It can be whatever pressure and temperature we're at. But we note here that we've used the ideal gas equation, right? Ideal gas law. So if we substitute that in here, then we arrive at the following. We can write that Z equals, and I'm going to put, RT over P here. So let's just put all of that together. So that would be RT divided by P. And if we rearrange that, that's going to be P times Vm divided by RT equals Z. So two different but similar ways that we could calculate Z. And what I want to note here is this Vm in this equation would still be our observed value. So there's a couple of qualifiers that we can put on this. When Z is equal to 1, that is our perfect ideal gas, right? So when the observed molar volume is identical to the ideal molar volume, Z is 1, that's an ideal gas. So if Z is greater than 1, That means the observed volume we have is greater than the ideal volume. That would owe to expansion. And expansion, that means repulsions are dominant. And the way that we would have repulsions being dominant, forcing those molecules closer and closer together, that would be achieved with high pressure. Okay. So as we increase the pressure of a gas sample, we're going to force the molecules closer and closer together. They're not going to like that very much. And the result will be that they occupy more volume than they would ideally. We could have Z less than 1. And of course, as we might guess, that would correspond to compression from attractive intermolecular forces. And this actually occurs at what I'll call a moderate pressure. So that moderate pressure being somewhere down here in this sweet spot. So now what that means for our ideal gases will actually occur at low pressure. This region right here where the molecules are sufficiently far enough away from each other that they're not experiencing their respective intermolecular forces. Okay? So Z equals 1, ideal gas, that happens at relatively low pressures. Z greater than 1, that owes to expansion from repulsive intermolecular forces, which occurs at high pressure. And Z less than 1 is achieved through compression or attractive intermolecular forces, which occurs at moderate pressures. Okay, so we're going to keep going down the rabbit hole with this compression factor, but I just wanted to have a standalone video on introducing what it is. Okay, I'll see you in the next one.